Hello and welcome to the Google Cloud Advanced Computing Community. Very happy to have everyone with us today for what I think is going to be a fascinating presentation and a little bit different from our programming so far. We've covered traditional high-performance computing, we've covered AI a lot, we've covered quantum computing a bit. This is about massive distributed scale computing today. I think you'll really find this interesting. It's a different modality of leveraging a vast amount of computational resources. And I think that you'll find that very interesting, as well as the kind of problems that it can help solve. First, a little bit about me and the community. I'm Jay Boisseau. I am the executive director of this community, if you will. I'm really an advanced computing strategist and outbound product manager at Google Cloud. I'm super happy to be the host of this community and working with such a great team and such great speakers on great topics to bring it to you. My personal interests are high performance computing, AI, quantum computing, and computing technologies in general. And we will cover all of these advanced computing technologies in this series. So what is this community? Well, first and foremost, it's a community of practice. It is all about the kind of information that will help all of you be successful in your careers and help make your organizations and companies successful by us sharing leading expertise and information from thought leaders and analysts and expert practitioners with you. And the purpose, of course, is to build expertise, your own expertise and the overall community expertise in ways that will help accelerate innovation and discovery. So how do we do it? Well, we build this community in a few ways. One is through these weekly online sessions that are live so that you can communicate with each other in chat and ask questions of the speakers that I will read at the end. And we really like that live feel to these webinars, although if you miss them, they are posted on YouTube on our channel later. But we encourage people to attend live because then you'll also be able to ask questions of each other and the speaker. We also have periodic in-person events because communities are strongest when we can sometimes get together in person. So we make sure that happens at the SC conferences, the ISC conferences, at Google Cloud Next, and then at other events that we schedule at Google offices around the country and later this year around the world. So we're very excited to have two ways to interact with you, online and in person. So who is this community for? Well, it's a community of practice, so you can guess that means it includes Google staff, of course, also our great partners, and also the customers and users of Google Cloud. And the intersection of those three groups makes up the heart of the Google Cloud Advanced Computing community. But it's open to absolutely everybody. It's open to analysts in the media, to potential customers, to potential partners, and to the general public at large, just people that are just interested in learning about these technologies, professionals, students, people in other careers that may be thinking about career changes and such. So we have a wonderfully diverse community of professionals and students and experts and novices in these sessions, and we welcome everyone. I should say also that we have a very good website for finding out about what's coming up and a great YouTube channel for seeing things that you might have missed. Now, not everything we do is recorded. The in-person events are not currently recorded. We're going to explore doing that, starting with our in-person workshop in April in New York City. But there will always be things in person that are difficult to impossible to capture in a recorded fashion. Some of the small group interactions, some of the labs, etc. So we really encourage you to attend the in-person events if you can, but for the weekly sessions, these will be posted to our YouTube channel. It usually takes us a few days to put them on there, but we encourage you to check out topics that you missed. And also please share the website and the YouTube channel with your colleagues. We have a lot of great content there. And this community is most successful in its mission if it reaches more people. So please help us out with that. Some quick community guidelines: professional conduct, of course, is expected, respectful communication, and our core principle is that we are here to learn. And that means respect that principle, enjoy the sessions, of course, enjoy communicating with each other in the chat features, but make sure and be respectful. Submit questions in the Q&A feature, which you can access from the 3x3 dots in the bottom right corner. I apologize that it's an extra click to get to it, but it's pretty easy to use. And finally, we do encourage you to use meet emojis. Use them sparingly. Don't distract the speaker with overuse of them, but absolutely use them when you think they've made a particularly great point. And at the end, there's an applause meet emoji as well. And if you're not sure what I'm talking about, the smiley face in the bottom center of your window, if you click on that, it will pull up a bunch of meet emojis. Generally, the ones on the left are good, and generally the ones on the right, we hope you won't use during our sessions. And with that, I'm very happy to introduce a colleague and friend, Dan Desjardins, the CEO and co-founder of Distributive. Dan, thanks for joining us.
Jay, thank you very much to you and Adan for making this possible. And I was reviewing some of the other speakers who are very distinguished on this channel, so it's an honor and imposter syndrome almost to be here. Yeah, but I'll share some stuff that I think is cool, and we'll let the audience decide for themselves. Do you want me to kick off with that?
Yeah, you can go ahead and share.
Okay, sharing now. And I do apologize, my share screen is a bit finicky, so if it kicks me off, anybody poke me with a stick and then I'll reshare. Is this all visible right now?
Yes.
Okay. Well, thank you everyone who made it. Today I'm going to talk a bit about an 8-year-old project now to do some massive distributed computing on the web stack, which 8 years ago it would have been called heresy. But with a lot of innovation in the WASM and web GPU space, it's starting to become stronger and stronger. The communities are rallying around these web technologies, and it's a bet that makes a lot of sense from a point of view of running anything, anywhere, at the same time with a lot of security guarantees that come from the web model. And so personally, I did a lot of compute back when I was doing research. I'm a computational physicist by background. I did a lot of electromagnetic modeling for non-destructive evaluation technologies, taught physics and space science, and spent a couple of years flying C-130 Hercs for Canadian search and rescue. And then I jumped into industry and, very fond of computing and technology in general, and inspired by the whole SETI at home concept, wanted to make a tool that I would have wanted to be able to use back when I was frying my laptop, running around, trying to compute, doing all this numerical integration and these big, gigantic batch jobs. So Distributive was born in 2017, based in Kingston, Ontario, Canada. We've been working humbly on our distributed computing software. It's not a wrapper around any of the existing distributed computing technologies like Kubernetes, Ray, HTC Condor, etc. It's a completely brand new framework called DCP, and we're a small but nimble team with former telco folks and former folks from the web browser communities. And we have a simple goal, and this was my own personal goal, is make it really easy to compute. I don't know why it's so hard, with all these layers of abstraction and DevOps and everything else. I found it personally frustrating that to compute on my laptop was easy, but the minute I wanted to use 2 laptops, suddenly there was a gigantic step function in skills and things I needed to learn. So we want a DevOps light or no DevOps distributed computing framework to allow people that want to specialize in physics or data science without becoming sysadmins, sysops, or DevOps engineers, to just say, here's my code, here's my data, here's my $5, go, and get me my results back. So, okay, what is DCP? It's a distributed computing framework, so there's nothing new about the concept of distributed computing, except that it's built on the web stack. And it builds in some directly into its fabric, payments and metering. So some of you are thinking, okay, isn't this just SETI at home 2.0? Yeah, in some ways it is. I mean, distributed computing is distributed computing. You take a workload, you split it up, you farm out the pieces, you collect the results. Yeah, that's been around for decades. But no, this is not SETI at home 2.0. We've really pushed to the edge the idea of running on literally everything. There is no device I can think of, or very few, that won't run the web stack. And the web has been designed to run any code anywhere, untrusted code securely. It's extremely sandboxed. And we know that because Google's put billions of dollars over the last couple of decades to make sure that people could surf, in Chrome without hitting malicious code, obviously that they don't download or interact with. If they're just surfing the web, it's an excellent security guarantee. So to make a compute platform out of those concepts just makes a lot of sense. By building native, like on the web stack, and unifying web and native execution environments, you can literally run CPU and GPU workloads anywhere, both in browser in a simple website, and we'll do this in the demo, but also GCP servers and everything in between. The other thing that we did that's different here, I mentioned earlier, I was naming Apache Spark, Ray, Kubernetes itself, etc. They're all mechanical. They take a workload, they split it into pieces, they bring the results back, and usually billing is instrumented around it or on the infrastructure in the first place. What we did is we put the billing and metering directly in, woven into the fabric of the system itself, which means that you can roll it out, this type of system, across any cluster of heterogeneous devices, and be able to do some meaningful billing and metering. And finally, I want to come back to the web security model. The web stack is the only stack that has as much money thrown at it for as much time as it has, that allows it to run any code, untrusted code, securely. And that is an absolute non-negotiable prerequisite for any form of compute sharing system. And if we think of the smart cities of the future, where different owners will own data and sensors and compute infrastructure, but everyone benefits from the gains, you're going to need a type of fusion of hardware and compute and sensors and data. And when it's owned all by the same owner, it's more easy to operate. But when different pieces are owned by different people, you need absolute security when you're going to engage in these borderless compute paradigms. So being built on the web stack is something that lends itself naturally and immediately to those needs. Okay, so back to the end user story. This is what I wish I had when I was doing my physics. What you see on the left is a straight up, very simple for loop in Python. And if you rewrite it as what you see on the right, it automatically will blow it out across as many nodes as are connected. And so take a little look at that, because I'm going to use an applied defense example in a second. But this is as easy as it should be. There's no DevOps here. There's no sysadminning. There's no right sizing. It's just take your loop, rewrite it like this, and voila, you can use thousands of nodes or however many are connected. And that was the true goal here, is to make it just so easy and effortless for people to do this, so that the platform itself gets out of the way of the scientists trying to get the results. So a little note on that. Everyone in the room here, being technical experts, understands that the limitations here is that we won't handle MPI workloads, because we're collecting together heterogeneous devices on loosely coupled networks. Well, that's not good if all we want to do is train neural networks. But it's great for a whole variety of other workloads, including batch inferencing and Monte Carlo statistical modeling, etc. And so this is the type that this type of system is well handled, as you all could have guessed. We don't, for security reasons, allow MPI flavored HPC workloads, because it would require opening up node-to-node communication in hospitals, universities, and other places, which we're working towards that, but cautiously. So that means that these workloads here are best left to true MPI HPC systems like Google HPC. So let's go to an applied example. And I did promise a demo, or Jay promised a demo, and I'll try and fulfill it here. This is a real Royal Canadian Air Force pilot staffing Monte Carlo simulation. It's open source code from defense and dummy data, so nothing here is being shared that's not allowed to be shared. But if we dig into to PycoMod on their GitHub, right at the bottom you see this for loop. And that thing is iterating over a whole bunch of reps that they want to do for their Monte Carlo simulations. And each simulation will take quite a long time. And when you want to run 10,000 of them, I was running it with 32 cores on GCP. It ran all night and it only finished about 30% just with 32 cores. So that's a perfect example where if you had 1,000 cores, you could finish this in a couple of minutes. But tapping into thousands of cores is, it's not that easy and it's not that cheap. Typically for non-expert users, but DCP is designed for this. So earlier I was showing you this loop on the left, and then if you rewrite it as you see on the right, then you can basically automatically burst it out horizontally. So it's small here, and people, if they want to come back to it later, can take a closer look. But here it is. The reps is the list of the runs, the Monte Carlo runs. And here it is. Job is DC. And we're in the, I promise this is the last of the boring, specifically technical stuff, and then we'll get into the hands-on demo. But this is it. The crux of it is the second line here, where DCP maps the build and run model with all of the arguments to each of the reps. And that's the parallel job. After that, you can decorate the job handle with specifics like compute groups and give it a name and all that other kind of uninteresting stuff. And at the end, you just call job.exec, results equals job.wait, and then everything comes back asynchronously. And then the results are correlated in the right order at the end, and voila. No need for, that's all the code that's needed for running this, this example. So in promising a demo, what I'm going to do now is I'm going to harvest compute from devices in today's audience. Through a website, and to be cute, we Google branded it. But we're also going to run in tandem here a GCP instance that will automatically connect to the Google Compute Group, and it'll create a hybrid edge cloud compute cluster. So let's spin that up. If you still see my screen here. I have some metadata in here that basically auto starts the DCP worker, connects to the right group, and some other configuration options. But all I have to do is hit start, and this thing will automatically connect and start pulling tasks from the scheduler. What I'm going to do though is I'm going to open this in a browser, and I'm going to look at as soon as it's started up. Meanwhile, can I ask the audience, don't worry, you're not downloading or installing anything, it's a single click, but if you open dcp.network on any device around you, and I did it here, and it should look like this, dcp.network, and then you'll see compute group, public or private. We're going to want to do private because this is going to be a private compute group for today's demo. Then all I have to do is hit start. And once you do that, you'll be pulling tasks from the network. I haven't deployed any jobs yet, so you won't see any. Meanwhile, I'm just going to connect to this VM.
Dan, did you say hit public or private? I'm sorry, which was it?
Private.
Private.
If you want to try public later, you can. You'll just get a bunch of public science jobs and other things. Okay, so I'm inside this VM, and I'm just looking. It looks like the worker is ready. I was doing some trials earlier, but there we go. It's connected and it's waiting for work. And now I'll deploy a job. So this is a job. Oh, oops. Can't find that because it doesn't exist. There, jobs, deploying, awaiting results, and that was it. And right now, there should be some devices doing work because I'm getting results as we see, and you can see they're all coming in asynchronously. And there you have it. That's a combination of the audience, and this this GCP worker doing a hybrid compute, edge and cloud. So that's a simple, that's my physics. That's actually was my PhD physics stuff that I was doing back in the day, numerical modeling. And we can deploy that defense demo as well, which I have here. And if I hit run on this, it will also go into that Google Compute group. Uploading, job accepted. And so there we go. Now we have two jobs. So we have a simple physics job, and we have this HR simulation model also running. This one is quite a bit longer, and it's several minutes per slice. So we're not going to see that probably anytime soon, but I'll come back to it later. Now, fun fact, while I was running that, it debited money from an account. And you can see here, this was 200,000 compute credits a few seconds ago until I hit refresh, and it decremented down because as I deployed these jobs, it pulled money out of, or I should say compute credits out of my bank account. And if I want more, then I have to buy more, and I can do that. Here's 10,000 more credits for like $3. I'm just showing this not to be cute, but because this is the economics part. And so people can, you know, punch in a credit card, and there you go. Now I'm back up to 209,000. So buy, spend, and then on the other side, all the workers, all of you folks running workers just now, have been collecting compute credits. Now, you're not getting them into your account because you haven't created one. If you did, they would be yours, and then you could turn around and you could sell those compute credits in the same way. Oh, and of course, I have to sell out of an account. And here I'm going to make $6. And there we go. I just made $6 minus the processor fee. So buy, sell, earn, spend, you know, as you'd expect in a compute economy. Okay, so going back to the presentation, let's be pessimistic. Cool demo, so what? The point is here that organizations anywhere can maintain a low total cost of ownership or a total core cost of ownership by combining sunk cost infrastructure they already have, consuming it to the max, and bursting to Google Cloud to supplement. And because DCP doesn't do MPI flavored HPC workloads, it's a perfect on-ramp for HPC MPI flavored workloads to Google Cloud as well. So an example would be a university, not Ivy League, but middle of the pack, for example, that doesn't have, you know, a supercomputer in their basement to do HTC style workloads and boost the capacity by going to Google Cloud, and also use up HPC for all the stuff that DCP is not set up to do. So it's augmenting compute capacity for overall very low costs because it's sunk cost hardware, and it's a natural on-ramp to cloud for most everything else. And there's an even bigger picture. We mentioned World Community Grid. We're partnered with World Community Grid, and they have like millions of devices that are capable of running the DCP worker inside their own BOINC clients. And so this sets up like a perfect, the ultimate hybrid compute continuum for global scale scientific computing workloads. And so this brings us back to the compute continuum. Imagine soaking up every cycle from every CPU and GPU, from constrained devices right at the edge to laptops and servers, all the way to you know, HPC cloud on the extreme right. And here I say, mirror, mirror on the wall, who has the most heterogeneous cluster of them all? And you know, being somewhat marketing here, this fridge on the left is actually doing computational physics, as is this Tesla on the right. Those would represent the extreme left of that compute continuum of you know, small, maybe uninteresting devices from a power perspective, but certainly interesting from a exploit all possible cycles perspective. all the way up to VR headsets. So this is the Oculus Rift doing compute using the goggles themselves. And then you can have smart boards or these educational display boards doing compute, because they have about 8 cores in each GPU. So lots of compute all around the place. And then for every possible environment, there's a worker node, whether it be in browser, which is quite interesting, to your standard Ubuntu, Docker, Windows, Android, etc. Workers. I'm leaving this slide for questions. It's security and architecture. It exists. We can talk about it. It's useful for doing deeper dives. But at the end of the day, we're running V8 and Dawn as the sandbox runtimes for these workloads. So the browser workers, this is what you just ran. It's our branded version of it. But I mean, basically, they can be embedded in literally any website anywhere. This one is very obvious. There's a button and everything else, but you could embed it, for example, in youtube.com or the New York Times or Vimeo or whatever. And then on an opt-in basis, you could allow people to do compute, or people could allow their machines to do compute while they're watching videos. Why? Well, maybe it's an interesting alternative to web ads. What if 160 million YouTube viewers were doing the transcoding for all the continuously new uploaded content, or for science, for lack of a commercial use case. 160 million nodes is a lot of compute. It's a lot of CPU and GPU that could be harvested while they're watching, cat videos or wherever else. And there's a saying, that clicks, right, ads built the internet. Well, I think tomorrow's internet will be paid for by cycles, and DCP is the perfect vehicle for this web scale compute. So how's it going? What are we doing? I'm kind of close to the end here. We've been putting this out for free to academic institutions. It's used by a number of hospitals to do some machine learning to optimize surgical schedules. Insurance companies use for batch optical character recognition, where they're trying to reconcile doctors' notes against prescriptions. Government of Canada just launched a call for DCP pilot, hence that defense demonstration I showed earlier. And we just signed an agreement to partner with an international OEM where they're going to operate their own branded version of this DCP platform and bring it to K-12 schools around the world. Here's oceans of compute reclaimed in Canada and Brazil. And we continue to expand. We have our sites on Mexico, and it's just hooking up compute everywhere. So the call to action is simple. If anyone saw anything interesting here, we want to talk to anyone and everyone. We want to bring more DCP plus cloud plus everything to more academic campuses. We want to collaborate and create new web scale compute business models, replace web advertising, or at least provide an alternative to it, for example. And we're looking for for loops. So if anyone has any interest in playing with this or doing something, let us know, because we're having fun building it and we're having fun deploying it, and we're just trying to do a lot of good for science, but also industry. Thank you.
All right, let's give Dan a round of applause. Thanks, everyone. Dan, we've got some questions for you. A couple have already been submitted, but I'm going to ask the first couple here based on one I saw in chat among the community. I want to make sure that everybody is comfortable with the security model. So to first order, wouldn't it be fair to say, look, your browsers are already running code, right? You rarely go to a static HTML website. Usually there's JavaScript and it's running some code locally in your browser anyway. This is a way for you to leverage the same security that's already built in to your browser, but make it easy for people to run their own applications, leveraging compute power via the browser, as opposed to just the JavaScript that ESPN.com or something runs on your thing. Is that a fair simplification?
It's the simplification we always use when explaining it to folks. It really helps get in front of the cybersecurity discussion. If hospitals have browsers on their computers, they're already operating the same security envelope that we are.
Yeah.
And then I get to layer on and say, I have 2,000 plus unpaid Google security analysts that are constantly patching, and making V8 and Dawn and Chrome better and more secure every single day. So we get to pull those patches and that security in. So we're standing on the shoulders of giants, of course, as we put this out here. But the concept's simple. People have put their trust in the web stack for moving and executing content. And so to make a compute platform out of it just made sense. And of course, for people following, WASI is making huge strides. Web GPU is starting to take over. It's device and GPU agnostic, etc. TensorFlow.js has a web GPU backend. Onyx Runtime has a web GPU backend. I won't be surprised to see JAX and maybe even PyTorch have a web GPU backend at some point. So it's the web stack is something you just can't bet against. And while you're speaking, I'm just going to reshare a screen. A pop-up just appeared, and these are the plots from the computational physics jobs that just completed on a bunch of people's phones in the GCP server. So there you go, hybrid edge cloud compute, delivering true results with a single click.
That's outstanding. Thank you. The second security question, and I think I love your answer to that. So I don't want anyone worrying about the security model. And thank you. We do take security very seriously, obviously at Google. So I'm glad you're riding on that effort in this. But there's a different thing to security, which is not data theft, data privacy, but just whether or not you want to allow somebody to use your cycles. Now, granted, they're idle if you don't use them, and once they're gone, they're gone forever. So really, most of us should want to make sure our cycles are doing something at least productive. But is there any risk of, and I know the answer already, but I'm going to phrase it as a question, is there any risk of somebody else harnessing your browser to run their physics code without your consent?
Well,
you kind of have to willingly go to their page to do it, right?
That's right. And I was thinking about how to tackle this question. So there's more to it. Like I showed everyone the really quick, like, oh, just go to this website, click start. But on an expanded screen, when it sizes down, it sort of cuts out some of the options that we're displaying. But if you go to it on a bigger screen, you'll see there's more options, like setting a minimum wage and other things. You can specify, like I have the GitHub link, but you can literally specify specific jobs that you only want to work on. So you can be very narrow and precise and surgical about what you want to allow done via a worker. You can set minimum wages that are not zero. So by default, I think everyone was running with a zero minimum wage, but you could set it to higher. So you can say my cycles aren't free. And this is how much I expect. This is the revenue model I expect per CPU second or GPU second or whatever. And if there's no work that satisfies it, then no work comes in, and so on and so forth. So yes, opt-in basis, but even more granular than that, with specific access controls and very granular business model controls, so that sets up an incentivized system for people to participate in.
Great. I was going to ask another question, but Kenny Moore has kind of asked it. Kenny says, I'm new to distributed computing. How different is this programming if someone is already used to running on HPC? That's part one. And then part two, and for myself, how do I get started with distributed computing in general? So before answering those, Dan, it might be good to put your URL in the chat window so that everybody can go to it to find more about distributive.network. Is that correct?
That's
distributive
correct.
network. And then Kenny wants to know, how can he learn more about distributed computing in general, and how different is it from HPC programming?
Well, Jay, this is like your and I's favorite topic. Like, what is HPC versus HTC and everything else? Well, there are purists in the audience, so I want to be careful how I put it, but HPC using message passing, MPI, you need InfiniBand and tightly coupled nodes, with a lot of memory and all this other stuff, right? And that's not what DCP here is designed for. It is designed to use all of the nodes, but not the high-speed interconnects. And so distributed computing is best described as being useful when you have a workload where every computation doesn't depend on every other computation. So if you're running a million simulations and you're tweaking the parameters ever so slightly, example, Department of Energy does a lot of HVAC modeling, where like the placement of the HVAC system and when you're designing and the architecture of a building will have an impact on efficiency. How do you figure out the optimal way to do that? You have to run a lot of simulations and kind of converge on the one that is going to be the most efficient. Same thing with, I don't know, you're making a new golf club, like, are you going to create every possible permutation of golf club, with a machine? No, you're going to simulate it, so you're going to tweak parameters. So these big, gigantic parameter sweeps, Monte Carlo simulations, hyperparameter tuning, batch inference, etc. Those are all examples of distributed workloads. So on distributive.network, there is a tab on the top right called suitability, and I'll actually run you through what it is and what it is not, what it's good for, what it isn't, and that's true in the general case of distributed computing. If you want to learn more, there's lots of stuff online. I'm also very personally happy to talk to you about it. But at the end of the day, if you have a for loop or nested for loops in your code somewhere where there's no recursion, i.e. the output of the last loop element isn't needed for the next one, then you can burst that horizontally.
And Kenny, I'm going to give my spin on that question as well, because as Dan said, there's purists who see it one way and other people see it a different. I would remind everybody that high performance computing didn't used to be MPI, distributed memory programming, and it may not be in the future. Again, high performance computing, the commonality is it's whatever technique you can use to get higher performance than mainstream computing. So in the early days, HPC was a Cray processor, was so much more powerful and expensive than any other processor. That alone was considered high performance computing. And then we introduced parallelism, and then we introduced message passing and such. But I look at high throughput computing as a modality of getting high performance that just it is suitable only for workloads that don't have to communicate in real time. They communicate only at the beginning or end of the process and not during. So thus MPI is not needed, and a client server model can distribute the workload and then collect the results. So that's the way that I would describe it. So to me, what Dan is doing is high performance computing. It's just for a certain modality of it. And in fact, many supercomputing centers that run largely MPI distributed memory applications also make allowances for running very large, high throughput workloads as well, because when that's the right tool, it's the right tool. And as long as all the workloads are part of the same actual overall science job or engineering job, it's still all related. It's still a high performance computing job, just run a different way. So I love what Dan is doing here, and I would defend it and say it absolutely is, but Dan knows that a lot of HPC purists would say, oh, if you're not doing MPI programming, it's not HPC. And I would just remind them that 40 years ago, they weren't doing MPI programming and it was HPC. So where would Kenny learn more about this, Dan, about distributed computing in general? You've given your URL for how to use your technology, but for understanding when a workload can be decomposed in a distributed, in an HTC fashion, as opposed to domain decomposed for MPI programming. Is there any resource that you would send Kenny or anyone else to for learning client server based distributed computing for high throughput computing workloads?
Well, if he has a workload in mind, I would straight up go to one of the LLMs and just start asking it questions like, hey, I'm doing this. Is this distributable? And it'll after you bonk it on the head a couple of times, it will probably spit out an answer that's close enough to being true. And then we'll see what it says. That being said, there are some interesting choices of words like distributed training. For neural networks sounds like it would be distributable because it says distributed, but it actually isn't. It just means they're using massive amounts of GPUs, but they are definitely on a high performance network. And there's a lot of barriers and synchronous computation happening, and it is not just distributed, right? So anyway, LLMs I found pretty good at giving a first order answer. And if you're not sure, you want to talk to me directly, definitely do. But that's what I would do. I'd use LLMs, and then I'd reach out, Dan at distributive.network, if you want to dive a bit deeper.
Sounds great. In terms of the kinds of workloads, I think either you mentioned Monte Carlo, or at least I heard it in the description you were given, and some other workloads. But one thing you mentioned was hospitals are using this. And by the way, if anyone's concerned about privacy and is not comforted by everything Dan and I have said, hospitals are using this, and they have among the very greatest security and privacy concerns. And Dan's already got customers using this, so that's how secure it is. But in the context of hospitals, you mentioned machine learning workloads. You didn't say whether they were deep learning neural net-based methods or more classical methods, but we had a question from Droen van Bemmel. He said, I may have missed it, but I didn't hear the word AI. Why is that? I heard machine learning. Can you talk a little bit about some of the machine learning and maybe other AI methods that Distributive.network supports?
As a keen ear, and that was deliberate, because I would be misrepresenting DCP if I said AI, because AI now, it means like training these, these neural networks and deep learning, etc. That requires MPI, HPC, and full stop, end of discussion. Classical machine learning, where you have, your gradient boost, linear regression, bagging, support vector machine, random forest. Those are more amenable, especially random forest, are more amenable to distributed computing. Not only are they more amenable, but they're also preferred in these settings, hospital settings, because they are observable and decidable. So an LLM can hallucinate, and you can't really backtrack and say, why did you suggest we, create a surgical schedule like this, right? Whereas if you have a classical machine learning algorithm, you can totally retrace why it made the decision it made, and that's still critical in the fields of medicine. Can you imagine if you were making prescriptions based on LLMs? And we're not there yet. but good old-fashioned machine learning, which all the cool kids have done away with. They're all like racing at PyTorch, right, to do their deep learning. You still need classical machine learning in situations where auditability, and clear lineage of decision is critical, because there's literally people's lives at stake, right? So anyway, so we're kind of lucky that in that niche, DCP hits like 4 or 5-fold. 1, keeps data private and on-prem. 2, it uses machines that are already bought and paid for, so there's 0 incremental, infrastructure costs of the hospital. 3, it luckily can do like the type of algorithms that are required for auditability and to support decision making in that realm. And 5, just throwing a free 5 one. It's super easy to deploy. It's deploy and forget. Once you deploy these workers, they self-configure with whatever dependencies are required on a job-by-job basis, and you don't have people having to reconfigure them every single time they want to do something different.
Yeah, speaking as Google Cloud and HPC and AI workloads and such, I'm a big advocate of this, because as much as I think large scale science and engineering and business applications can use huge on-prem or cloud systems like ours, it does make sense to leverage everything you've got locally for the workloads that can support that. And the majority of the compute cycles in the world are not used for HPC applications. It's a big market. It's a $50–60 billion global market, but it's a hundreds of billions of dollar IT market for cycles. And much of that is single-threaded compute stuff, or multi-threaded but single-core compute stuff that can run in this kind of fashion. So absolutely makes sense to do this. And then, Dan, I think it'd be fair to say, even if you have a research application that is amenable to an HTC modality of HPC, because it's research, you may still need far more than everything you've got locally, but this gives you the option to use everything you've got locally and then only buy as much more as you need, as opposed to buy all the cycles for the entire workload while leaving some local cycles idle doing nothing. So it's a good optimization. Your hybrid example, I think, is a great illustration of that. Use everything local and then buy what you need on top of that.
And as a former recovering physicist and researcher, there's no such thing as too much compute. I'm always going to want to make my triangles smaller, right? And so, of course, you'll saturate everything you have, and you'll still use more, right? So, yeah, what I'd like to do is bring this to every academic campus, in the world. It should be free. It is free for academic campuses. Unlock that compute, and where this really makes a difference, like the long tail. The Ivy Leagues do have their supercomputers, but the long tail of not have-nots, but less haves. Like this is perfect because it out of the box, and then it can also slowly bring people also to cloud for all the really, really important HPC MPI stuff that DCP just isn't designed to do. So it's a nice marriage between cloud and on-prem edge and just unlocking value, like in general, for society.
Yeah. Well, with that, let's give Dan another round of applause. Thanks, everybody, for tuning in for Dan's presentation. I have a few more final slides that I hope you'll stay for. We'll make them real quick. We have some upcoming events, some great ones, including next week. Dan Ernst from NVIDIA will be here to talk about how to effectively use NVIDIA's different GPUs for HPC and AI applications. So it's not going to be just an HPC talk or just an AI talk or just a generative AI talk. We really are going to talk about how to use NVIDIA's hardware and also lots of their software for a diverse set of HPC and AI applications. And we're seeing a lot of that in the science and engineering communities, the need to merge simulation models and data analytics models with AI. Also, want to remind everybody we have a great website, so please go to that website and subscribe to the mailing list. We only send out 1 or 2 emails a week about upcoming events specifically. There's no advertising for any products. There's no giving away email addresses or anything. So we hope you'll sign up, and that makes sure you don't miss any of the live sessions. It also makes sure you can register for in-person events, especially before they fill up. So we hope you'll sign up for that emailing list. And again, check out our YouTube channel. This talk and many others are on that YouTube channel. Many of them are easy listens as podcasts. The slides always help, but some of our events don't have slides, and others that do, the speakers are so eloquent and so familiar with the content that they're able to describe things in a way that you could listen to it in podcast format as well. I also want to give a huge shout out to the awesome team that works behind the scenes to bring all of these events together, make sure we're able to execute them. You'll meet them at the in-person events too, because they're often instructors in that. So please give a round of applause for the Google Cloud Advanced Computing Community team. And with that, I want to thank all of you. I hope you have a potential collaborative things here soon. Adnan and I look forward to talking to you. I hope people will reach out to Dan if they think that their organization or enterprise could leverage this technology to offload some of their on-prem computing work to. And of course, as Dan showed you, he can make this scale into Google Cloud and other clouds as well when your needs exceed the full utilization of all of your local resources. Thanks, everyone. Have a great week.